So what is COOCK? COOCK stands for Collectief Onderzoek en Ontwikkeling en Collectieve Kennisverspreiding. So it's about doing use cases together, doing research and development, but also about sharing and transferring knowledge. So it's a collaboration between research institutes and companies. Like I said, the COOCK project Open City wants to document the knowledge we as research institutes have about data management, data disclosure, data standardization, and translate this into best practices. Like this session will be about best practices for the open data part of an open city. And then afterwards, we can apply this more to concrete business cases. The COOCK focuses on environmental data or factors such as the air, sound, electromagnetic radiation, etc. And it's important that all these domains are standardized in an open data setting. In today's workshop, one of the contexts I see this happening is the Open Data Charter. It already exists a few years now, I think, and it has some principles about sharing open data. One of them is that the metadatering, adding metadata to the data has to happen as close as possible to the original source. That's something we will discuss in this workshop in more detail, how we can do this, make this source really authentic and reusable for others. Also, point 9, it must be open and machine readable by using machine readable formats and standards. We also discussed this in more detail later. It should be using linked open data for these authentic sources, so others can reuse this more easily and provide links to them. Niels will talk about that in his introduction to linked open data. Also, point 12 is you should use the web as a first publication platform, so this decentral architecture of the web can be used. And also point 13, we see in the charter that the data should be as real-time as possible, and also historic data should be available. But in this point is like mentioned, it's focusing on sensor data, but it's not only about sensor data, it's about all kinds of data, also addresses, buildings. They all should be like as real-time as possible, so others can that the latency towards others can be as low as possible. So in our second presentation today, we will talk about the technique that will be applicable not only to sensor data, but also to slower data. So I want to do a quick poll. Does your organization share or consume linked open data today? I will first ask one of them. It's my first time I use a poll in Teams, so I hope this works. Can you all see the poll? So the question is, does your organization publish or share linked open data?
Yeah, you must open the chat in order to see it. Yeah.
All right, let's already see 12 responses. More than 64% of you already published linked open data, which is very good, of course. In the meantime, I will open the other poll. And that's about if your organization consumes linked open data. So the other way around. Okay, also more than half of you are consuming, some maybe. All right. I will leave this poll open until the end of the session. In this workshop, this is an overview of the COOCK offering of our research institutes. It's about open smart city platform, environmental data, and application domains. We will talk about mostly about the platform side. What kinds of architectures can we shape for sensor data, but also slower data, and how can we standardize that? Also, at the end, we will briefly discuss what types of modeling approaches can we do, more specifically with AI solutions. In our next presentation, Niels will talk about what is linked open data to give a basic introduction to the topic. Afterwards, we will go more in depth with best practices with sharing data. I will do this together with Pieter Kolpaert. And then we'll end with From High Quality Data to Reliable AI by Bart Braam of ID Lab Antwerp. And then we have a quick wrap up where you can ask questions. So I give the floor to Niels now.
Thanks very much, Brecht. I'm going to share my slides like this. I hope that works for you. Then I can still keep an eye on the chat. If there are any questions, please don't hesitate. So I'm Niels Walraven. I'm a senior researcher at IMEC and at Smith at the Free University of Brussels. And I worked on the Smart Flanders program a couple of years back, where we wrote the charter together with the 13 center cities of Flanders that Brecht just referenced. So this is some stuff that we've been working on for quite some time. What I'm going to share with you today is I'm very happy to see that there are already 12 organizations / people here that publish open data, linked open data. But I'm still going to give a sort of general introduction into what open data is, what linked open data is, for those of you who might not be fully aware. So bear with me. I won't take up too much of the time here. But just to start with open data, just an example. We're all familiar with this type of view in Google Maps. You're being presented with sort of real-time assessment of how busy it is when you plan a route and when you want to drive home, for example. That's where I live in Antwerp. This data is collected from mostly from Android devices, right, that are stuck in traffic, that are not moving, and Google is using that information from all of its devices that it has out there to give you sort of an assessment of how busy it might be on your route. But you have other examples in that same application like this. So this is around my corner where I live, and this is the weekly market. So this is it indicates that the street is blocked, but only on Friday mornings. So this would be too complex to gather from all of those Android devices that are out there, and this is basically done using open data. So this is a publicly available stream of open data, basically using an API. This is still the old version. There's a new version available in the meantime. The Flemish government, basically, whenever there's an intervention in the public space, whether that's a market or people moving house, blocking the street, when there are events, when there are roadworks that are planned, that information is entered into one database by local authorities, which is then published as open data, and which other organizations, like in this case Google, also in their Waze application, uses to add to their information that they give you about that public space and about whether a road might be blocked or not. It's the planned works. It's not real-time data, but it can give you an indication, and definitely for stuff that has a weekly occurrence, for example, like a local market, that can be very useful information. So that is what open data basically can do. There's basically two requirements, general requirements, principles when we talk about open data. The first one is there's an open license that's linked to the data that basically explains what you can actually do with the data. So it's a legal document to some extent. It can be a legal document that explains what you can actually do with the data, and in the case of an open license, that actually allows you to actually do something with the data, of course. And the second basic principle is that the data is made available in an open and machine-readable format. So can I actually do something with the data? We don't want unstructured data, for example, locked in a PDF. We don't want images. We rather want data, structured data that we can actually do something with, and of course, preferably in an open format. So we have a relatively strict definition of when we talk about open data. It's not always completely used in the correct way, this concept. So we want to stress this, that there's an open license on the data, and that we have the data published in an open and machine-readable format, and that allows you to actually do something with those data. Tim Berners-Lee, who famously, as you might know, invented the World Wide Web, came up with this sort of classification of open data. So it's the also relatively famous 5 stars of open data. The example that I just gave, or the definition that we use, is basically 3 stars of open data. And I'll walk you through them quickly. When you just make your information available on the web in whatever format, you do that under an open license. That's our first principle. You have 1 star open data. If you make it available as structured data, for example, in a Microsoft Excel file rather than in an image scan, we talk about 2-star open data. And if you then also make it available in a non-proprietary open format, using, for example, comma-separated value file instead of Excel, then we talk about 3-star open data. And this is sort of our definition of open data. But we're mostly here to talk about those next set of stars, linked open data, basically. And so I'm going to explain a little bit what that is at the conceptual level. So just to be clear, I don't have a technical background. I'm a communications scientist, but that's also, I think, why I was invited to this talk, to give this sort of from a non-technical perspective, to explain you something that is basically technical. So we're going to delve into those 4 and 5 stars of open data. So what are those? So let's get a little bit technical. At the conceptual level, when I want to share data between 2 systems, you basically need to agree on a protocol, and you need to agree on what type of questions you can ask a different system to get a response also in a timely manner. And so if you agree on a protocol, your system can ask questions based on that protocol according to the rules that are defined in there. But if you want to scale that up, that can become a challenge. If you have your system and you want to query all kinds of different systems on the web, the challenge becomes that you need to agree on protocols across all of those different systems. And so in order to maximize reuse and increase interoperability, that really becomes the challenge in this type of context. So how can we ask more complex questions on the raw data in this type of more decentralized information system? And that obviously means that you need forms of interoperability. And there are many different levels of interoperability when we're thinking about this. And it refers back to some of those basic principles that I also already discussed. So at the first step, you have this legal interoperability, which we have an answer for. If you have an open data license resting on those pieces of information, you can achieve legal interoperability. If we use a proper license, then we know what we can do with those data. Technical interoperability, we need a way to exchange information. Well, thankfully, we have the internet, we have the web, and HTTP is sort of the uniform interface in order to exchange that information with each other. Then at the level of the syntax of the way that the data is structured, we also need interoperability. And that's that idea of having open and machine readable formats like JSON, XML, CSV. We have open standards in order to structure those data. And then at the semantic level, this fourth level of interoperability, therein still lies somewhat of a challenge. And that's basically the idea behind linked open data, is trying to solve this. How do we at the semantic level understand what data means and what the contents of those data means? So truly at that semantic level. And we have part of the solution definitely at the technical level. We have URIs, which I'll explain in a second, in order to tackle this level of interoperability. So this is a piece of information in three different formats. So this is at the level of the syntax, a table, as you might know, a JSON, an XML describing the same pieces of information, saying that the St. Peter Square is a parking in Ghent, and Ghent has a population of 275,000 inhabitants. So this is basically the same information structured in the same way. If you want to move towards linked open data, what we want to do first is break up that information, that data, to its most atomic level, basically. And this is where that idea of semantics really comes in. It refers to language, basically. It's breaking down your data into these triple structures that are structured in the same way, where you always have a subject, a predicate, and an object. So you have something that you say something about, basically. These are short sentences, your information at the most atomic level, saying, for example, St. Peter Square is a parking, St. Peter Square is in a city, in Ghent, and Ghent has a population of this many inhabitants. Suppose we have three machines publishing three different facts on the web. So you have one machine that publishes a bit of information saying St. Peter Square is a parking, St. Peter Square is in Ghent. You already see that it's written in two different ways at the St. Peter's plan part. And Ghent has a population of this many. These three pieces of information are on the web, and machines can reason on this. If you build a client, for example, that wants to query the web for all the available parking garages in cities that have a population over 250K, machines can reason on this and can provide you with an answer. But that does mean that they need to find all of these bits and pieces of information. And so that's where this semantic challenge comes in. When I say St. Peter's plan, how do I know I'm not talking about the St. Peter Square in Rome versus the one in Ghent, for example? When I know that we're in Ghent, how do I know that I'm not talking about the actual physical square or the parking garage that is underneath that square? And this is basically where URIs come in. And so the idea here is that at that most atomic level, those bits and pieces of information, that you don't describe those using your own identifiers, but that you describe those using URIs. And so these are basically links on the web, not dissimilar to URLs, basically. So uniform resource identifiers, using those links on the web in order to identify those bits and pieces of data. And so when we say St. Peter's plan, there's the city of Ghent publishes this information as linked open data. So if I were to follow this link, I would arrive at a website that gives me the information about this parking site, but that is underlying also readable for machines. So it's both readable for people and machines. And you have the same for these pieces of syntax, like for example, is also available on the web. You also have then big vocabularies that describe all kinds of pieces about the world, basically. For example, parking site, that is also available as a link on the web. And so rather than building databases that use your own identifiers, numbers, for example, you could use different types of IDs. The basic premise idea behind linked open data is that we use links on the web in order to describe data at this most atomic level. And that's basically what linked open data is, and that's also all it is. So it's using these links in order to point to information. And that makes it much more easy for clients, for intelligent clients, to retrieve this information across the web. It allows for much more automation also, much less manual work, because these links can point to each other, and if they're structured in the correct way, you can very easily retrieve the information that you need in your client. So it's about coming up with, of course, a strategy to define those URIs. So if you want to start today, it's about thinking, checking if URIs are available, if those links are available, reusing those, and so using URIs instead of your own closed identifiers, and using RDF whenever possible. And so definitely, and that's what's also included in the Open Data Charter, when you're using, but also when you're building, if you're the government, authentic sources, for example, this really comes in handy. And so information that's reused a lot, think about addresses, think about those interventions in the public space, it really pays off to publish this as linked open data, because it allows for this automation to take place much more easily. And also when there are updates to the data, they will be automatically retrieved as well, rather than having to republish them, for example. So that's at the technical level. We can solve this, but there are also other levels of interoperability that come into play, of course. This means that you need to make good agreements with defining these URIs, using proper URIs. There has to be a strategy behind that. The Flemish government, for example, has a strategy behind the URIs that they use. But it needs to, at these levels also, you need to consider interoperability, basically. So between organizations, between business processes, we want these data to be reused as much as possible. So it's also building awareness around that. And finally, making sure that there is an impact and that you do this exercise for data sets that are being reused a lot. So I had 15 minutes. I think I'm in my time to give you sort of a general introduction for those of you who weren't fully aware on what linked data are. You have my contact details here. I'm not sure, Brecht, if we're taking questions now or after.
We'll take afterwards.
Yeah, okay. So thanks for your time. If there's any questions, I'm here until noon.
Or feel free to use the chat, of course.
Yeah.
Thanks, Niels. Now we're all on the same line. What is linked open data? Let me just upload my presentation. Voila. So for the next presentation, we'll talk about best practices with sharing data with third parties. As we all know, more and more environment data becomes available. And you can see here on the picture, this is the ID Lab home lab, where we test different kinds of sensors. And that can be, for example, radiation, but also air quality or sound. These are all important aspects for a more healthier life. So in this workshop, we want to discuss how sensor data can be shared towards the open city in order that policymakers can make better decisions. It's also important that the same sharing strategy can be used for slower data. For example, that there's a tree or many trees are planted around your home to give an indicator of how much nature is there. These kinds of data sets are becoming semantically interoperable. In Flanders, we have the Oslo program, the Open Standards for Linked Organizations, that provides different semantic data models for different domains. A new trajectory has started, the Oslo Air and Water model, which of course focuses on air and water. And I invite you to join one of these workshops so we can have in Flanders a proper air and water application profile and vocabulary. This is important for background noise. This is important that we use the same terms for example, for sensor observations. What is an observation? What is a result, etc. So the next workshop is the 4th of March. You can also question, becomes this data technically interoperable? On this level, we have, or the API level, we have different standards that exist. One of them is NGSI. This is a context information management system and allows to create and update digital copies of entities in the real world. You can see it as a REST API specification that uses JSON-LD, so linked data in its core. However, there are some limitations. For example, hypermedia principles are not applied, which means that applications will need to write a sequence of hard-coded requests to manipulate the data. And also HTTP caching, one of the main benefits of the web, is not applied, which means that it's not foolproof in an open data context, where you can have thousands of clients asking the real-time data, for example. So NGSI LD is mostly fit for context management. So you can do CRUD operations, you can read, you can update, you can delete certain attributes of an entity, or you can retrieve changes over a certain time window, which we call a temporal query. Although will not be enough for real Open City domain questions, as this requires extra processing steps. For example, if your sensor is not calibrated, you need to do some post-processing steps. And you also will need different kinds of data sets. For example, here we have a digital twin of a city where you can see traffic intensity. For these innovative applications, sensor data alone is not enough. You need to retrieve more context data from different APIs. For example, there can be base registries that contain where are the buildings located, how high is the building, what is the breadth of the streets, are there canyon effects? So you need different types of data for these applications. And to do this, we need to integrate these APIs. For example, OpenStreetMap offers data dumps, or you can retrieve data from the Overpass API. This is a specific query language API. Or if you want to use the 3D GRB-gebouw LLD1 API, there's a different type of API for that. Also for HEBOT, like Niels mentioned, for the roadworks, you have an API for that. So it requires a lot of manpower to transform this data into your application scheme and making sure you have the latest version available. Like in the middle picture, you can see that the home lab is not there in the data set. So this is definitely an attention point we should have in an Open City initiative to make sure that all the actors can easily retrieve the latest version of things. So what we see as an Open City approach is where you have on the blue side a reusable query engine library. This can be used by all different applications. These applications have their own logic and should be able to just ask a certain question. Give me all the sensor data in a certain region, for example. And this query engine will then do dynamic interface-specific requests to all the different heterogeneous interfaces and will provide the results back as a stream to your application. So you don't have to invent the wheel yourself every time. Below you can see you have a solid pod where data of citizens is stored. You have a context broker where technology vendors store their context data, and a base registry of a government instance, for example, the buildings registry. All these different types of data sets will be needed. And we can align on the semantic part already with Oslo, for example. But on the API level, we have different kinds of API. We have LDP API with solids. We have an NGSI LD with the context broker. We have a REST API with the base registry. And what we do is apply a small layer of linked data on top of that. For NGSI-LD, we have an NGSI-LDF approach, which we will talk about later in this presentation, or the event stream API approach. And this allows other actors to synchronize with that data to their architecture. And above you can see the context broker of another technology vendor, and he synchronizes this data with the eldest client, we call this, to make more specific APIs, for example, the Sparkle and the geospatial index. But we'll talk about that more in depth in the next slides. So first in this presentation, we'll talk about the event stream API and how other indexes can be built on top of that. Then we will talk about the eldest clients to synchronize with event streams and how this works with Communica. That is a reusable query engine. And finally, we'll talk about NGSI LDF to also support event streams on top of NGSI LD. I'll give the floor to Peter now.
Yes, thank you, Brett. There's quite some echo from your side.
Okay, really?
Yeah. Yes, okay, perfect. I should be able to take control of the slides. Yes, I see that works. Good. So what I want to introduce here is once after the presentation of Niels, once you have linked data, there are still some decisions that you need to take. And one of the most important decisions probably is what web APIs are you going to put on top of your data set so that you can publish it for everyone to reuse for any kind of purpose possible. And this brings me to this question: what should be the core API? So what should be the API if all your funding is gone? Or like you only have the bare minimum of your funding anymore because maybe you don't have projects, maybe there's some austerity in government. I don't know. Let's just a thought experiment. I'm not saying that's going to happen, but just a thought experiment. Then what's the minimum API that still should be online so that at least your data is still accessible? And many people already thought about this specific question, and then they came up with answers like this. For example, you have a WFS, which is an OGC standard for geospatial querying. Now they're evolving towards the OGC API, but that's still the same, a very similar interface. And now the OGC API will contain linked data, which is a nice add-on. But still, you can ask very specific geospatial queries, and you will get a very specific answer. But WFS, a web feature service, is really interesting for creating GIS applications. So if you want to create an application showing a map, selecting features in a geospatial area, this WFS is the perfect API for you. The only problem is that from the moment you want to ask graph queries, like queries trying to find connections between entities and so on, then you need a graph query language, and Sparkle is a graph query language for RDF data. So people also started to publish Sparkle endpoints. For example, in the city of Ghent, you can find stad.gent/Sparkle. In Vlaanderen, you can find data.vlaanderen.be/Sparkle, and you will get a Sparkle endpoint in which you can give a Sparkle query, and you will get a very specific answer back. And as a dataset publisher, you can ask yourself, but which of these very specific APIs should I be able to host? And probably all of them, because then I will give any flexibility to reusers. But that's hardly feasible. And I call this also the maintenance hell. You will get into more and more APIs that you will need to keep online, and these are not evolvable, because once you put one online, it should always be backwards compatible, and it should be always be kept available, because there could be some application that still depends on it. So you need to keep it online. And then you get into a getting the lights on or keeping the lights on syndrome, where you just spend all of your budget on just maintaining legacy APIs, and you don't have any freedom anymore to put some of the budget into innovation. So as an alternative to that, because over here now I put auto-completion, because now it may be that you as a third party, you want to do auto-completion across certain parts in your data set. Then and that API was not available. So what do? Well, you need to set it up on your own system, the auto-completion API, and you will need to download the data dump. So you will not go through an API, you will just download the data dump and get it onto your own system. There's another problem here. This is a replication problem, because everyone will take copies of your data, will put it into their own system, and will do updates on their own system. For example, a good example that I found from working with the people working on the address registry at the Agency of Information Flanders. It's now called Digital Flanders, I must say. That is with the address registry is that different municipalities started to take a copy of the address registry on their own system. And from the moment, for example, that 2 years ago, I think there was the merger of different municipalities. So we had 308 municipalities, but we went to 300 municipalities. When that happened, then they just applied these changes locally in their own copy of the data set, and didn't sync correctly anymore with the original data source. So there you get what I call a replication hell. You get out of sync data dumps that happen everywhere, with local changes happening, and which are not perfectly in sync with the true data set. In order to solve that, I think we need to go towards event streaming. We should stop sharing data dumps itself, but we should start treating data sets as an always growing append-only interface, so a log where you keep adding the latest version of the object at the end, so that everyone in the ecosystem can always sync and can always replicate the last objects on your data set, and everyone has an equal access to creating their own very specific querying interface on top of that. But this is not where the vision stops, because if you, for example, have this address registry, and you can apply it on the address registry, but equally as well on an air quality data set, for example, I'll get into that. But then this event streaming approach, well, you could imagine that you have different actors there. If this event stream is the base of that, you can imagine that you also fragment this linked data event stream into geospatial tiles, for example. If you have this geospatial tiles that you put on it, then, for example, for the address registry, you will be able to say, I want street names in Bruges, for example. That means that you don't need to download the tiles from Hasselt, because that's not at all relevant for your data set at that time. So you can just download the tiles around Bruges and keep in sync with these things over there. Another intermediary or reusable index that you can put on it is, for example, a version materialization. And a version materialization is something that data dumps often default to. So so you don't keep the entire history, you only keep the latest version, and you create data dump from that and you put it publicly. The problem is that you then cannot ask questions across historical data, or you cannot also ask question across what changed or how did it go. This is really interesting for air quality observations, of course, as well, because there you certainly want to do queries across how did the air quality evolve over time. So this is what you cannot do with data dumps, of course, or with version materializations of these things. And based on, so the linked data event streams goes towards the reusable indexes, creating, for example, tiles, but on top of these tiles, then you can build your querying interfaces. So this shield is what we see as a priority list. It's something that you should focus on as a data publisher, first getting your linked data event stream in order, then stimulating the ecosystem to build extra indexes on top of them by doing a part yourself, and then also hosting a couple of querying interfaces on top of that yourself. For example, then this specific OGC API, a Sparkle endpoint, and so on. But you will never say that you will all keep that online forever. Because if that disappears, then a data reuser can always decide to host that Sparkle endpoint on their own servers, because there are reusable indexes and there is a linked data event stream on which they can build such thing. So this then looks like this. You have the linked data event stream that is on the top. This one gets by third parties or by the publisher itself or by the third parties. So these indexes can be done by intermediaries or by the data publisher or the data consumer itself. They can build public fragmentations of that event stream, geospatial, but also based on text or based on time. For example, you can say, I have a specific validation on top of an air quality data set that I want to put public right here, and I fragment it in geospatial areas. Well, that can be put in the first fragmentation, and then a WFS API at the third party side can reuse that in order to speed up querying. This is really interesting, but because this architecture will allow to put the right processing where the funding for that processing is located. A data publisher should be funded or has as a core task to do the lifecycle management of their objects. So if an object changes, you have the task to make sure that everyone in your ecosystem and your reuse ecosystem has that update, has that last version as fast as possible, but can also access the history of your data in the way that you see as your core task. Then the intermediaries, well, you may have an organization that is in charge of making sure that certain queries are answered faster. For example, a certain governmental institution that is working on finances, for example, they could create a very specific index for finances, but could make it public so that all the their reusers are also able to benefit from that specific index to create then specific APIs that are hosted at the third parties themselves. Good. So what is an event stream? Well, an event stream is a collection of immutable objects. So these objects will never change anymore. So they're version objects. For context information or for slow data, as we call it, like buildings, street names, addresses, taxonomies, and so on, these would be version objects. So a specific version of an address at a specific time, so that you can go back and say, at that time, that version was true, and that thing, I will never have to download it again, because once I download it, it will never update again. That's an immutable object. But they say, we are a version of a more abstract concept. For example, the address that can be materialized into a specific version if you're interested at a version at a specific time, for example. The same idea of these immutable objects can also be true for air quality observations, where you can have specific versions of the observations. For example, this is a sensor observation of sensor A that says, I'm the version 1 of this observation. Then sensor B puts something on it. Then C, and then A again. So this A again, this could be a calibration. For example, you could say afterwards, well, there was some problems with that sensor, so we will do a correction, and this is the new version in hindsight that we found of this air quality measurement. Good. So this core API, so this collection of immutable objects, this is the one that must be findable, accessible, interoperable, and reusable. I think this is the core API that everyone should publish first, and that should be the core API of any open data set, whether it's fast moving like air quality data. Well, it's not that fast moving. Do you know what I mean? And then the address data set, which is slower moving, it only has a couple of updates each day. We have, so Brecht earlier mentioned that this NGSI specification, it doesn't do hypermedia. Well, this is what we do, what we want to do at the core. So we want to document in this from the moment that you have a first page of an event stream, that you would be able to follow links. Just follow links towards the rest of the collection. So we define the concept of a collection. This collection has a certain schema or shape, which is linked over here. So it's always documented that the collection, for example, is a collection of observations, which means that you, for example, will have a SOSA result time, that you will have an observed property or a feature of interest, and then you have a sensor, which is then the context information, like all the sensors that you have installed. You have feature of interest, observed properties, and so on. So this collection will then have a specific view, which is a kind of pagination. So you can then say, look, all these objects are earlier in time. If you go back in time, and you can find the next page. If a client is interested, you just have to follow that link. And this is how it looks in linked data. So the same explanation holds true here. We just say, look, this is an event stream. It's an event stream of all outdoor air quality measured by company X. It is validated by a certain shape, which you can find over here. Over here, we use Shackle to do it. If you don't know Shackle, you should certainly check out the book Validating RDF. It's a great book that explains everything about how to validate RDF data or linked data. It says in this collection there are a couple of objects in here, and I have a view. This is my page one. This page one has a certain relation to a previous page. It says I have a less than relation based on the results time, so the result time of my objects, and all the objects in starting from page 2, they will be less than or earlier than this specific timestamp. So this way, your code can understand whether it should download this page or not. Because if you already downloaded, observations that were earlier than this, then you don't need to do it again. And for example, if you only have a question about the latest observations, then you certainly don't need to follow that page again. And this is something new. This is the idea of hypermedia. This is making sure that your code can take decisions whether to follow the next page link or not. So instead of just having a next page link, we actually qualify the relation between this page and the next page by explaining what you can find on that next page. And I say pagination. Pagination usually works with next and previous page link, but over here, well, you can actually build a tree and you can have multiple relations. So you can have this is less than, this is greater than, this is in a certain geospatial area, this is an aggregation, and so on and so forth. So then it doesn't become just a simple pagination. Then it really becomes a tree. Hence the name or the prefix that we now use here is the tree relations that we put on it. Good. So a simple example of what you implemented before is on air quality data. On air quality data, well, we just did a linked data event stream on top of it, where you can just download the next page link and you can quickly show it in a graph, for example. It doesn't go, creating this graph doesn't go instantaneously, no, because you need to do multiple HTTP requests and you really have access to the raw data, which is on a minutely level. So of course this goes slow because it is a lot of data. But anyone now can create a resampling on top of this, or can create aggregations or statistical summaries on top of this. So this is what becomes possible with linked data event streams. And well, this code that we wrote now to just visualize this one, this can be put on top of any data set because, well, it's just following links. So we abstract we make an abstraction from the concept of how to fragment over here. Good. So your core of the things that you should host is your linked data event stream. You can host indexes on top of that yourself. These indexes then can again be described using this tree vocabulary, as I said, because now instead of just saying, well, the next objects will be later in time, we can also say, well, based on the SOSA has feature of interest and there the WKT string, which is a geospatial shape that I can find, or geospatial polygon that I can find in this thing. Well, I will say that all their WKT strings will be inside this polygon that I document over here. So if I follow tile 2/page 1, that will make sure that I will have a subset of the data that is in a specific geospatial area, which means that if I'm interested in only the updates in Bruges, that for whether it's addresses or whether it's air quality, I will just be able to follow links, will find my own path through the information architecture, and I will be able to find the right data just in time. What makes that really interesting is for the data publisher itself, this thing. Why should you do hypermedia? Well, this is because your entire ecosystem of reusers will always interpret your links, which means that if you change your links, you will be able to be backwards compatible. Your system will always, or the reusers will always find a certain path. If you remove a certain API or if you remove a certain index because you have to lower your because your budget lowered, for example, then you can just turn off intermediary indexes. So in this second layer here, you can just turn off or turn on new indexes. If you turn on new indexes, your ecosystem will be happy because they will be able to, for free, answer certain queries in a more fast fashion. Do you have less budget? You can turn off certain indexes, and then, of course, the third parties will need to organize themselves to maybe host a couple of these interfaces themselves. And maybe they will be able to because they have sufficient funding at the reuse site in order to create these indexes. So this is really a story about separation of concerns, making sure that you can perform the functionality on top of your data set where the right funding for that specific functionality is located. Good. Yeah, this is an example of the geospatial fragmentation that we implemented as well, and we submitted as a paper as well. So, and in order to show that this can be done quite efficiently. If we're now applying these ideas to context brokers and to real-time data management in a city, I think the task that, or the exercise that was done in the project, or the City of Things project data broker, is really interesting because they really asked the right questions. They did the right scoping towards what does it mean to set up a data broker, which is still quite broad, but they really want to do time series analysis, want to make sure that you can do certain aggregations, and at the same time, while it should have time series functionality, you should also be able to have context and also query that context efficiently, which were always two completely different worlds that come together, like an address database that you then need to combine with air quality and sensor data. The architecture which I took from the City of Things project data broker. So this is in the deliverables of that project. It was created by Gert de Tand. I think Gert de Tand was also in the attendee list. So we can ask him questions afterwards about this as well. But the components are really interesting that are put inside this data broker. I think it's the work here has been done meticulously, so it was done in a good detail. I think it's feature complete, but I think one thing one thing that we could do better in this story is make sure that every component that is put in here can also be decentralized and can also should also be able to be taken up by someone else. So let's look at an architecture that we just created very recently and this is a really simplified version that I want to start presenting. This is the first time I present this, but I hope that this kind of architecture will be able to be presented more and more. Is that data providers, well, they can put data inside a certain system, but they should at some moment first make sure that it is published as a linked data event stream. This linked data event stream, well, you can have projections on top of that. So projections are small, it can be linking to another source. It can be aligning it with a different standard. It can be anonymizing. It can be a quality check. It can be an archival task. It can be a fragmentation or an index, creating an index on top of that specific data. It can be many things, and these projections get published as a derived linked data event stream again. So then these data consumers, they can try to automatically find their way through this entire ecosystem of hypermedia links, which starts all from a core event stream, and where you will see all the derived indexes that have been built on top of that event stream. And these interfaces, they should be able to automatically translate their very specific queries to which fragments of data that I need to download from the ecosystem. And this is something that we now try to automate with the Communica SDK. So Communica is an SDK written in TypeScript that you can already use to try to query over this entire ecosystem. It's still also it's both research as already a stable platform that can already be used. So look into communica.dev. It is certainly an interesting querying structure. It can already do auto-completion queries, Sparkle queries, and GraphQL queries. The specification of linked data event streams, this is now being adopted on a European level by the CEMIC program. So we will be able to, if you're interested into hosting your data itself as an event stream, take a look at this location. You will be able to have a really easy explanation with a couple of examples of how to do it. Of course, creating a linked data event stream should be as easy as possible. So we try to also keep this specification as lightweight as possible in order for many people being able to get into linked data publishing as fast as possible from their core and raw data that they can publish. That's it. Brecht, I think this is your cue now.
Yes, thanks. So we have still 15 minutes to continue in this presentation. Now I will be talking about the Communica engine in more detail and how the LDIS clients works. So Communica is many things. It's invented to solve Sparkle querying as its main task in the beginning. Why? Because there's a need to have a modular query engine where you can create specific building blocks for specific query tasks. The problem that there was in the beginning was that people make new branches in their GitHub repository, for example, to implement specific features. For example, I want to do link traversal, but these features didn't get back to the main branch, and so quickly there were different setups created, and it was difficult to compare query engines together with each other. So that's why Communica was invented. So you can have a semantic configuration how your engine works, and that you can easily replace a certain building block with another building block. And it allows to query heterogeneous interfaces, for example, data dumps, TPF endpoints, Sparkle endpoints, so all different kinds of linked data APIs, and also in a federated fashion. So and And of course, we can apply this Communica ID and tooling also for the event stream ecosystem, where we not only want to do graph querying with Sparkle, but also do synchronization jobs so that data can get from one system to another. Or we want to do text search on top of an index that has been created. Or maybe you want to do a time series query on top of the linked data. So also it has to happen in a modular way. It has to have a reusable semantic configuration. And I want to query over the core event streams and over the indexes, or maybe to specific query indexes. It uses the actor model. And an actor does a specific task. For example, you have a JSON-LD parsing actor to parse JSON-LD, or if there's an actor for turtle, that's another format. You can also have actors that extract metadata. For example, the tree metadata that retrieves the hypermedia links to the other fragments. Also Hydra, that's another hypermedia standard. You can also write an actor for that. And this way, logic is separated in independent building blocks. But it's not only about actors, it's also about mediators and buses. So a bus is actually a thing, actors that do a similar thing, like the parsing thing. One does JSON-LD, the other one does turtle. These can be grouped together with one bus. The bus can be called parse RDF. And then you have a mediator that will select the best actor for the job. So from left to the right, you see actor 0 has some RDF data, and that needs to be parsed. Then it will ask the mediator, oh, okay, I want this data to be parsed. Which one will be the best one to do this? Then he will go to the bus where the actors are subscribed. He will send a test message to all the actors to see which one will provide the best answer, and then he will pick the best actor, and in this case is the actor 3. Now, to give this bit of more concrete example, a mediator can be a fast mediator. This means that it will pick the fastest actor. It can also be a combine actor that will combine the results of all the actors together. You have different types of mediators. This one is the fastest one. So it will send a test to the parse bus. And this one will send it to all the actors that are subscribed. Here, test this. And then we'll give back, oh, this is a slow actor, this is a fast actor. And now the mediator can pick the one that is preferred and then return the answer to the actor. And this way we can have a modular system where you can replace or add new actors to the system. To wire this all together with semantic configuration files, we use components.js. It's a new JavaScript or TypeScript library where you can do dependency injection. So you configure and declare how your actors, your mediators and buses look like. And then you have a setup configuration where you really instantiate all your actors. Where you can, like a play box, pick the actors that you want for your query jobs. So if you want more information, there's a lot of tutorials about this where we go step by step through the code on communica.dev. So one example is the event stream client, as you saw on the Open City approach slide, or the eldest client. So that's a Communica client I'm building. So if you have a database with your own API, you can easily retrieve all the events from an event stream with this client. What you configure is, this is the entry point. This is the starting URL of the event stream. This was the last time I synced with this event stream. This is the format I want to retrieve it. And this is some JSON-LD context I want to apply on it. So these kind of options are will be possible in the nearby future. We also, because it's Communica, we can share these building blocks with different query engines. We have on the one side the generic, the LDES client, and that uses the hypermedia actor to retrieve the three members, the three relations, which you can see in the middle here. This can also be used by other query engines, such as the type ahead text search engine we're also writing. For the indexing from the event stream to the index, we also have tools available. The Termin Network Server refragments a stream on text, so you can do prefix queries on top of that. Also, the tree index library allows to refragment geospatially or on a time index. This is an example of an or text search query engine in production in the Netherlands. Netwerk Digitale Erfgoed has multiple taxonomies for concepts. And now with this query engine, you can ask a certain string over multiple data sets in a decentral way. As you can see on the right side, it downloads all the right fragments to give back the proper results. So you can check this out in production. We also did this on OSM, OpenStreetMap, and GeoNames, so geographical databases. This also works decentral. Both have a prefix index where we can query over. Now, for the last part of the presentation, I will talk and explain how NGSI LDF works and how you can start playing with it. It started from the data broker project of City of Things. And on the architecture, what you want to do is, if you have a context broker as output, which you can see on the right side, we want to expose an RDF, linked data API, on top of that, and more specifically with the event stream specification. So how does this work? You are able to fetch geotemporal tiles, and this is an example around the City of Ghent center tile. You can give it a page query parameter. This is the time component, so the hour bucket you want to retrieve data. And also you need to give it the type parameter for because NGSI-LD expects that parameter. And this will give you back the linked data event stream for that tile in that time window. What happens internally is that it fetches all the modified at times for the entities in that region and time. So you can see here the /temporal/entities. That's the NGSI-LD temporal query interface. So it fills in that region, that time. Then it will fetch all the entities and the modified ads from that. And we will fetch every entity again with that modified ad to have really a snapshot from that moment of that object. And what is optionally is that we can convert the whole structure to key values. That's also an NGSI-LD thing that simplifies the graph into, it removes the metadata model of NGSI-LD, so we can have RDF as we mostly know it, not with the property graph model of NGSI. And then we repackage it in an event stream version object. So that's the approach we're taking. I've written some tutorials about this, which you can find on the following link on the link time series GitHub repository. And it's about first part about semantics in general, and understanding vocabularies. Then you can set up a context broker with Oslo data, and then we'll set up a linked data event stream on top of the context broker. So 3 parts. So the semantics part, we explain how RDF works. We will describe a building in JSON-LD and how we can describe the vocabulary terms of a building with RDFS, the RDF schema. That's what Oslo also uses to describe its vocabularies. And we will do the same exercise with NGSI-LD metadata model, which is a kind of different way of defining terms than RDFS. Then we set up a context broker with the Oslo data. We use the COOCK, the library in Ghent as example, where we use the Oslo application profile for the building registry to describe the geometry and the name of the building. We NGSI-LDFI, I call it like that, the COOCK. Why? Because Oslo uses RDFS, and I converted to the NGSI-LD metadata model because that is needed for the context broker to ingest the data. Then we'll set up a Scorpio context broker and then ingest and fetch the COOCK as example how that works. Then the last tutorial is about setting up the event stream on top of the context broker. It uses the NGSI-LDF software code we provide. It's of course not production code to use, but it's to give a general understanding how this works, and which allows you to fetch the linked data fragment, the geotemporal tile containing the COOCK. And this way you can see how the tree hypermedia metadata looks like, so you can navigate through the structure and maybe add more buildings inside the context broker to have more data. Next optional steps for these tutorials are to create a text index with the tools I mentioned previously, and that we can have a search application on top of it, like with the Netwerk Digitaal Erfgoed. So to conclude, if you want to expose an event stream API on top of your API, we're definitely interested to help you out. Or maybe you want to collaborate on the event stream microservice architecture, where you can have different projections, you can have aggregations, linking to objects, calibration APIs, event stream APIs on top of it. Maybe you want to create a time series client that uses Communica to query over air, sound, radiation, or maybe you have another idea that you want to discuss about in this workshop. So as key takeaways, linked data event streams should be your first priority as data publisher. So this allows that third parties can set up a sync with these data sets, create their own query engines, or create indexes for the ecosystem. And also complex query tasks can be performed with Communica. And in the next presentation with Bart, he will discuss more how this data can be used then in context-aware AI applications. So we're nicely on time, I see. If there is already one question you may ask, and otherwise we'll go to the next presentation, and then you can still ask some questions. Maybe Bart, you can already load up your presentation.
Okay.
Or feel free to ask in the chat.
Okay, so shall I continue, Brecht?
Yes, yeah, floor is yours.
Okay, thank you. So good morning, everyone. Let me continue the magic theme with an introduction of how to go from high quality data to the reliable AI. And first and foremost, what I will do today is introduce you to AI in general from a city perspective. So rest assured, I will try to be very much practical, but also not too detailed. And let me start by saying that AI It's a kind of magic. What I really want to help you answer today is how can you use this magic in an open city? Now, like all great stories with magic, some caution is needed. And also, you have to be aware that it's not always magic, right? There's a reality behind it. And so let's start with a real example. And I want to continue on the topics highlighted today, namely air quality. I will take the case of an air quality sensor provider who requests information from its sensors, of course, and who is looking into answering a tender. This is a fictive example, by the way, this is fiction, and who wonders, can I add more virtual sensors? So they know that the cost of installing sensors in a city is quite high, and so they wonder, can I provide more virtual sensors? Meaning, if I have a number of sensors in a city, can I then use the magic of AI to add more sensors? But those are virtual, they are based on models. They know that all kinds of agencies and scientists have very cool models. Can we use those to somehow do a smart interpolation in a city instead of buying and installing real hardware? And so they wonder, can AI help? First and foremost, AI. Very quickly, AI is used for everything. It's one of the top hypes of the moment. And let's perhaps already make a first distinction. You have narrow intelligence and general intelligence. General intelligence, that's quite simple in AI. That's anything a human can do. And narrow intelligence, that's perhaps a smart speaker or a self-driving car, web search, AI in farming, in factories, Industry 4.0. To the left, with the narrow intelligence, those are very narrow solutions. They can only do so much, meaning your self-driving car will not be able to answer your smart speaker questions. Perhaps there might be smart speaker tech included, but that's a separate component. Your web search, the Google system is really cool, but it will not be able to help you automate a factory. On the other hand, there's a general intelligence, which is the AI which can do anything. And it's the answer there is quite easy. We're not there yet, and perhaps that's even good. That's more of a philosophical question, but we do not have general intelligence, meaning all of our intelligence today is narrow. Narrow, it has a scope, it has potential, but it also has limitations. Important because, of course, if you want to consider implementing AI in your business, for example, in an open city, you have to be aware of the limitations. There's also a number of intelligence solutions, and I'm going to pick out a number of aspects there. Very quickly, you have the more semantical intelligence, or you have the machine learning intelligence. If you look at semantical intelligence, then you deduct from knowledge. So you go top down. You start from a full world view and you go top down, which also, by the way, nicely aligns with what my colleagues presented earlier on. On the other hand, you have the machine learning, and in machine learning, you are using inductive reasoning, meaning you learn from simple, small facts, small observations, actually, and then you build up facts and knowledge. This is very much bottom up. Both are valid approaches, but they are very different. And you should be aware of the difference also in when you start implementing. You should be considering, can I use a more semantical approach? Can I use existing knowledge, or should I try to develop new knowledge? Now, you might wonder, why is all of this AI happening today? Well, of course, you can say, yeah, I do it because my competitors also do it, but there are more reasons to it. First and foremost, of course, computational resources. Today, in particular with cloud resources, the possibilities and opportunities of introducing AI are large. You can easily start AI. Let me add one remark there. You have to wonder whether you should do it, whether someone else should supply it to you, but you can easily start it because there's so much computational power available today. Also, and we had lots of acronyms in the previous talks already, there's quite a lot of algorithms today. TensorFlow, Spark, there's a lot of solutions out there which you can start using. It's not always clear which are the right ones, and that's of course the challenge, but there's a lot of out there today which is already shared. Finally, and this is what also reflects on the open city paradigm, there's training data. AI needs data. AI needs data to learn. It needs to be exposed to certain truths in order to learn. And that is also the availability of that source is very broad today. And that is an interesting opportunity. Now, AI can do a lot. And this is a dangerous slide because it's not magic. A lot can be done, but you have to be aware about the possibilities. What can be done? For example, you can do really modeling and prediction, meaning reasoning, planning, predicting certain outcomes. You can do perception, and that's computer vision, the classical examples of recognize the people in the picture, recognize the car, etc. You can do natural language processing. There's quite a lot possible these days with chatbots, etc. It's not per se a data question there, but it's very interesting. And you can also see that quite a lot of cities are exploring trajectories as to interfacing with chatbots instead of a really, let's say, the civil servants. And finally, also very fascinating is generation, is having AI generate new solutions. You could imagine certain solutions being generated instead of and having, let's say, an almost creative or seemingly creative AI system instead of people doing it. And so there's a lot of possibilities, but you really have to wonder, are they feasible? And that is a question which we as AI researchers get a lot. Can I now just use AI? I want to use AI. Can we start it tomorrow? Yesterday? There's quite some caveats to be made. And let me walk you through those because we believe that it is important to be aware of those before even starting trajectories. First and foremost, it's all about the data. And lots of it. AI needs data. AI needs a lot of data. And there already you can see some advantages. For example, for our air quality project, right? There is quite a lot of data already out there today. This is really also referring more to the big data, right? And preferably this data is structured. For AI, and it's just like, let's say, regular students in a way, if a machine needs to learn, it needs structured data. A student needs structured knowledge. So preferably you have a database, a very big one. But it could also be, for example, a data catalog or similar entries from a city or a region. It could be Wikipedia, which could help you, and this refers a bit to the previous presentations, of course, which could help you structure certain knowledge. You could say, what about natural language? What about, for example, if you look at air quality, what if you ask people, how do you feel about the weather today? And you ask people, could you describe the weather? Natural language, that's already quite hard because then you need to start interpreting the language. Again, you could do so with NLP, which is natural language processing, but it will be harder. And already you will be introducing layers of AI systems where if you look at it that way, you already understand, what would be the quality of it? What would be the reliability of it? Also, what is preferably needed is labels. You want to somehow indicate to your system what it wants and how it wants it. If you really have just unstructured data where the system has to find its way, where you in essence drop the student and say, figure it out, that's much harder than if you can say to the student, well, if you do this, then that will happen. So structured data, labeled data. But also you need examples. You need good examples. And a very important one there is data quality. There we rely on the not so philosophical paradigm, garbage in, garbage out. And it's quite simple. If you start with a bad sensor, if you start with bad data, then no doubt about it, you cannot improve it. So you should start from high quality data. For example, if you look at air quality sensors, there's this project called Luftdaten, which publishes open data on air quality. They advocate the SDS 011 sensor. Well, the founders also say several studies indicate a good correlation with professional equipment. That's an important starting point. If you do not have sufficiently high quality data to start from, it's not going to work, because in essence, the truth, what you're looking for, is not in there. So the system cannot learn it. Also, you need representative data. And so what is meant by this is that you should be training, you should be learning your system to reason on the data with all kinds of environments and contexts. For example, if you look at air quality data, and it was mentioned before already, you have this phenomenon of street canyons, so very narrow streets with high buildings at the sides. If you expect your data, your model, to somehow reason about it, to somehow show the quality in these kinds of streets, it needs to learn. So it needs to be exposed to this kind of data. If you say, I want to only look at squares, well, then you need some other data. Also, the question is a bit, what about calibrated or raw data? Should your system output calibrated data, then best probably to also input calibrated data. Should you also take into account calibration? Should the system somehow calibrate itself? Then probably you need to also expose the system to the underlying data. So you need to expose it to raw data. Another interesting phenomenon, for example, for air quality, is seasonality, and it also goes to completely different aspects as well. Seasonality, so meaning, is there a certain pattern underlying in the data? For example, for air quality, if it rains, the bad air particles will of course rain down. So you probably need to train your system with rainy days and sunny days. But there's of course also winter, where it's much colder, and there's, for example, the peak of summer where temperature is much higher. Does that have an impact? If yes, then also train it. And of course, this is the example of air quality, that's logical. But for example, if you look at the examples of traffic from the first presentation, of course, you need to feed the system with data from both weekdays and weekends. Traffic is different, of course. And then the harder questions arise. What if no data is available? Can you train a system somehow to reason if no data is available? This is a hard one, but sometimes it works. Sometimes it works if you can somehow simulate it, if you can build a simulated world. If you want to put a rover on Mars, then probably you cannot fully train it on Mars. So you will probably need to simulate certain aspects and then go further. And so really, there's all kinds of solutions there. But most important takeaways here are: make sure your data is representative and make sure to tackle the different aspects of your data. It's not just the data set, it's not just a database, it really needs to be representative. Next step is, of course, context. And this is really where we see the added value of an open city. Can you add more information? Of course, you can say, well, this is a square, this is a canyon. But after a while, well, will you manually do that? Or could you link up? Could you use linked data, and could you add information on the geographical information, on the context, on the nearby buildings? Could you perhaps even use more linked data from other sources? For example, I have referred here to the data.gov.be, the Belgian open data, where you can see that IRCEL publishes open data with a specific license, where you can really link up to. So can you feed the model more? That would be really interesting. And this is exactly where we also believe that if you look at AI, the system needs data. You cannot provide all data yourself. So best to link up with more data. Be aware, just dumping more data in an AI model will not fix it. You will probably need a data scientist who can look at it, and where he or she can then say, this is relevant, this is not relevant. So it does not guarantee more quality, but it is valuable. And it is more valuable if you can automate it, if you can really link it up. Also, you have to be aware about, let's say, transforming your solution from one region to another one. The typical example is you try to do it in a lab and then you go outside. that will not work. The conditions in the lab are different. If you do it indoor, there will not be too much wind, I assume. Outdoors, it might really be a lot of wind. And that's the domain of transfer learning. So you can try to transform your knowledge, your model from one system to another. But you really should take care. A new sensor cannot always feed an older model, because the model might really have learned a certain situation and is then completely confused too, because it's exposed to a completely different situation. Again, it's like if you have a student learning and you expose him or her to a completely different teacher with a completely different way of looking at things, they will be confused. There needs to be a certain kind of alignment. Also, the context cannot always match, so it's really hard. Now, to make this a bit more specific, if you look at this, these are 3 different Belgian cities. Left is Antwerp, center is Leuven, and right is not Belgium, but is the beautiful city of New York. They're all close to water. Well, in Leuven, it's just a river, right? And in New York, well, it's not a river, but it's a very big one. And in Antwerp, yeah, there's the River Scheldt, which is very big, according to the people from Antwerp, of course. But you will notice that, for example, there's different street patterns. In New York, you have the traditional checker-like and very square streets and corners. Well, if you look at the city of Leuven or Antwerp, those are very much the historical cities with very narrow, winding streets. And so can you then just take your solution from Antwerp and move it to Leuven? No, probably. Although if you look at it, the different markets are already different, and the River Scheldt has a different influence, so you should take care. Can you move it to New York? Well, it's completely different. So you should take care of those differences. And what does it mean in practice? Probably you'll have to partially retrain your model. You'll have to add new information. You'll have to adapt. You'll have to make sure that it becomes stable again. Okay, but yeah, how given this knowledge, how then to tackle this? What should we do? Well, you should, of course, make sure that your experts who know what is going on there, that they are informed and that they are well in the loop. For an AI project, like any other IT project, right, you should not just drop it with the technical experts. No, you should make sure to hand it over, but to keep your experts in the loop. Also, you should make sure that you keep following it up, that you keep the information in there, and that you rely on the experts to model the data. But again, doing the feedback with your experts and your users and the city. They will probably also know that for certain areas there's a very windy corner there. They should also know, and they should be in the loop. Now, how does it look like in practice? I mean, what does this AI thing mean for me and my business in an open city? Well, let's look at the very, very, very simplified picture of AI in practice, and that's the pipeline. How does it work? Well, first, if you set up AI, in essence, what you're building is a model. And a model, it's kind of a black box where you feed all kinds of information and then it generates results. So what you will do in the first phase is you will train it. You need training data. Again, that's the need for data. This training data is fed in the model and the model will learn. Now, it's a bit more complicated. Probably your data scientists will split this training data in training data itself and also then a validation set, a set of data to test, is the model really performing? Because you can only input so much, you need to make sure that it works. Again, referring to the student model, well, you need to make sure that you test from time to time your student, because in essence you want to work. You want to learn, is he or she really performing well? Is he or she learning the right things? Okay, well, that should work. But then there's this, there's just a single word here, pre-processing. Very important. You will notice that once you start an AI project, lots and lots of effort will be put in pre-processing. According to some, 80 or 90% of your time, of the initial time, will be spent on pre-processing, meaning getting the data in shape. I must say that in the case of an open city, you have a slight advantage here, because in the case of an open city, quite a lot of pre-processing is done by inputting the data in the right standards. So that's good. You will add more context, so that can already help. But still, do not underestimate the pre-processing step. And then you can input the real data into the model and it will generate results. Is it that easy? No, it's even more complicated, because of course there's the question, well, what about the model? What is the model? Well, it's some kind of a system which you may know is modeled after neural networks in the brain. You input it and then it runs, and then out comes the result. Well, that's nice, but it's of course a bit more complicated. First and foremost, this model will run somewhere on a GPU, meaning either on-site or off-site in the cloud. So very often you will need to start talking to your solution provider. You will need to start talking to someone who can provide the GPU, who can make sure that this infrastructure, this hardware is there. Also, it's not just a matter of dumping the data in some kind of an automagic solution and it works. This model, the structure of the neurons, etc., will not delve into detail there. It's also very much a field of expertise in itself, meaning you have people in industry and in research who are really experts in picking the right architecture, as they call it. It's not the data architecture, it's not the network architecture, no, it's the AI architecture. It's really how do you structure the model, how do you make sure that things come in and come out. And they also have a whole bunch of acronyms like CNNs and RNNs, all kinds of technical details there, which I'm not going to dive into today. But important to know that you need an expert to look at your data, to look at the possibilities, and to start the training. And then they need to more or less evaluate. They need to see, can we get to a certain quality? Can we then scale it up? Can we improve the quality? And what will be the results? So this is quite a simple model, but do not forget, it can get quite complicated soon. And I will come back to it later, but you should remember that you need experts there, and also that you probably need to think about the infrastructure. Now, I wanted to make sure that you also are aware of certain upcoming trends, because honestly, this is a very simple model, but it allows you to understand what is upcoming. And first and foremost, I talked about the hardware, about the GPUs. To the left is a traditional AI, which we see today. And that's AI in the cloud, in a data center, either yours or somewhere more centrally, which is nice. But honestly, AI is moving to the edge. And what do we mean by the edge? Well, you have certain definitions of the edge. But for example, a smartwatch or a smartphone is already a good example of the edge. It's really nearby you. There is certain intelligence. This is, let's say, more in the health space, but also in an open city, we're noticing this kind of solution. And what we really notice is that sensors, including the one on the left and also to a certain degree the one on the right, have smart included. They have certain reasoning, certain logic included. And of course, this logic needs to be power efficient, because otherwise you cannot run it on the scale of a USB plug. So it really needs to be efficient. So today already algorithms are being moved to the edge. It comes with certain advantages, for example, being privacy aware, being power efficient. So there's certain advantages, but also challenges, because if it's that easy, why don't we always do it? Well, it's not that easy. So this is an interesting trend to remember. Edge AI, low power AI, this is certainly where we are going. A second upcoming trend, is explainability. To the right, you have a very crude picture of AI today. It's a black box. And to a certain degree, we do not know what is happening in there. To the left, you have a very classical decision tree. In this case, should you wear a jacket or not? And the left is very simple to interpret, and it's also very simple to have really good, well-argumented decisions, because you can see, right? Humidity, is it high or low? And you can really easily make a decision. To the right, you have a black box. So in essence, it will give you certain answers. It's like the magic 8-ball, which I showed earlier, if you noticed. But the question is a bit, why did it do that? And so the new field of explainability, or new upcoming field of explainability, is really trying to make sure that you can understand. And so if you're looking at AI for your business in an open city, you should be aware of this, because you might wonder, will my business need explainability? Can I confidently make certain decisions without really knowing the inner details or not? Sometimes you can, sometimes you cannot. Of course, explainability comes with added needs, added requirements. It comes with a certain overhead, no doubt about it, but there is some potential there. So that's an interesting one to consider. I explained you lots of challenges, and you'll probably by now realize it's hard, but now what? And I think for a good AI project to start from, I wanted to offer you the perspective of looking at the relationships. And I wanted you to offer the perspective from a simple acronym, which you will be able to understand, namely DUCS. If you look at AI in an open city, you should look at the data. You will be providing open data and or the open city, meaning you probably have some data in your business which you generate, which you consume, which you somehow consume from someone else. Also, there's the open city. Again, there might be a lot available there, so try to link up there. There's the users. Who is your eventual customer? It's still business, right? So you need to align with your customer. That's not to forget, make sure your AI answers business questions from your users. There's the context. Again, there's the added value of linked data. Make sure that you try to link up with that one. And why not also contribute to it? Because then, of course, you will be even more embedded within the open city and it could generate more business. There's the knowledge. AI is only as clever as your domain expert. Make sure to include your experts. Make sure that your AI answers the right questions and that the outcomes are relevant and are correct. Your expert, no doubt about it, he or she will be able to look at outcomes of the AI model and say, this makes sense, or this is really nonsensical. Make sure to do the check and make sure to involve your experts. And finally, you need solution providers. It is very hard to start AI from scratch internally. We saw it with a lot of companies, with a lot of institutes. Make sure to involve experts, either industrial or academic. Make sure to involve those to really be facilitated in helping in getting the right solution. Because again, there's a lot of complex technical details underlying these models, the pipeline which I showed. Make sure to have an expert solution provider on board. And so really try to remember the DUCS model for your next or your first AI model. I hope I inspired you, perhaps I confused you. In any case, if you want to know more about AI in an open city, let's talk. You can reach me via this email address, and let's hope to, by this, to realize magic together. Thank you.
Thank you, Bart, for your clever presentation and giving a high-level overview of AI. Are there questions from the audience?
Yes, I may have one question. What is already there? First of all, thank you for the very good and nice presentation. But what is already there in cities in general over the world from this kind of linked data sets? And is it already widely being used, or is it rather a research push which is just going on, or what is their division?
Who should answer that question, Brecht? Are you going to divert it to the right person?
It's about the linked open data used in the cities, you mean?
Yeah. So the question, maybe I will take it then. So the question, if I understood it well, is like, okay, this is now a presentation that given by a couple of fancy researchers from fancy IMAC. What does it mean like worldwide? How is this? Is this already something that is happening worldwide as well? Well, I can tell the story from where I know know it best. It's at the European Commission right now, which is also trying to engage different member states into adopting certain principles. And about raising the data quality, of course, or the usability of the data towards third parties. What they now did in Europe so far is set up data portals. So you have data portals everywhere. And it was a big promise because data was the new oil, and it's going to change the world. Millions of companies are going to start reusing open data sets. So you can find, for example, at opendata.vlaanderen.be, at data.gov.be, which was also mentioned on a slide somewhere, on European Data Portal.eu. You also have the European Data Portal that harvests all of the member states' data portals, because that's now everyone must have a data portal, and puts it in one big pile of ugly CSV and Excel data sets that you can start reusing. Now, I think the idea is good, like trying to make sure that you have all these open data sets, that companies can start reusing them. But I think there's a big gap there. The biggest gap is how, as a company, can you now find your way through this wilderness and chaos of data sets that are sometimes not maintained anymore at all. They're just part of a small project put on the data portal and not looked after anymore. Some data sets are maintained, then called, for example, reference data sets or base registries. You cannot like finding a complete list over Europe. That's just unfeasible. Like how can we create, for example, a view of all the addresses across the entire Europe? There's no common line in it. There's no. So I think we just must make sure that we have some minimal principles across all the member states to make sure that we can move forward. And Europe is now investing heavily in that. I must say, Europe, it's of course a really also in itself a lot of organizations that do not always talk to each other. So there is a certain stream in the European Commission that is really working hard on linked data principles. That's like the ISA Square. So it's also the CEMIC program of the European Commission at DG Digit. They are now setting core vocabularies, which are then adopted by member states. For example, you have in the Netherlands, you have Het Kadaster, for example, that is now doing that is fully published as linked data. I will actually I even find that a better example than our Flemish data sets, but I will. Yeah, so this is the link to that linked data. It's a great data set. You can do awesome queries on it. You can just see it as a table, as you're used to. You can do graph queries on top of it. It's awesome to play with. The same thing we have in Flanders, and we also have a standardization activity on that. It's called the Oslo vocabularies, which makes sure that we can standardize it. And then there's an entire program to also make sure that the local municipalities that they can also work with that data. And you see that happening everywhere in Europe a bit, but everyone is using is evolving at their own pace, is publishing their own thing. Like in Spain, you have the city Santander, who is doing awesome work on their open data portal, but at the same time also moving forward with NGS-ILD. So, and this NGS-ILD idea, well, it conflicts a bit right now with the open data world because it's not entirely the same. And how do you publish open data from NGS-ILD and so on? And I think this is now the bridge that we're now trying to make from our research perspective. So we see cities move at a certain pace. We see Europe moving at a certain pace. We see Flanders and the Netherlands and so on move at a certain pace towards linked data, because I don't see there's another solution to giving companies the freedom and the power of data to automate their data adoption. I think it's the only way forward to go towards just documentation. And I think linked data is the ultimate documentation of your data. But we see people move at different paces. There's this NGS ILD thing that does link data, but not entirely. So we try with our developments right now, which then are in a research stage, but we hope now by explaining this to you today, that companies can slowly also start adopting when, one, they publish data for a government instance, that they can also take these principles into account. But on the other hand, if you want to build a business on top of this open data, that you also won't code against one specific API, but that you will code against a data ecosystem, and that you will say, okay, I will follow links in order to find an answer to my question, so that your system becomes evolvable and that you can automatically find new data sets when following links, and that your system will become smarter as you go. I think that's a lengthy answer to your question, or was it not entirely sufficient, Ben?
No, I think it's more than sufficient and much further than that. It was even for the second question, who is investing in it? But yeah, you mentioned it also. So thank you.
So if there are no questions further, I have a poll I also want to do, just some general questions. You can see it now on the chat. The question is, how relevant was this workshop for your company or organization in general? Some feedback for the COOCK project. And a second one is, how likely will you reuse this knowledge? Right. So to conclude, what's next? It would be interesting to know what are your concrete challenges as a company, so that our next workshops of the COOCK, we can focus more on those challenges. Also, if you want to take up a project to build a use case, let us know what your ambitions are or available data set assets you want to expose. So after this, the next workshop is the 9th of March. It's about IoT and air quality in cities. It has two parts together with Vito and IMEC-NL. So after that, then we will do some learnings from international and local smart city initiatives, where we also be part of it, about the City of Things, data broker, ANPR projects, etc. Then Ugent Waves will also talk about healthy indoor quality of living, together with the Ugent. Yeah, you can find all this information on the COOCK websites, on the Vloga Kennis Hub. You can find the link above. So if you want to do a project one-on-one, send me a mail to have some quick talking, or want to collaborate on a bigger project. There are some possibilities with the COOCK, so let me know. if you have still some questions for Peter, Niels, or Bart, now's your time. You have still 3 minutes before lunch.
Yeah, if not, then we disappear forever. No. You can also still always email us, of course, through firstname.lastname@imac.be. Yeah.
Indeed. Thank you for your time and hope to see you soon in real life.
Bye.
Yeah. Thanks for organizing, Brecht. See y'all.
You're welcome.
Thank you.
Bye, everyone.
Thank you. Bye-bye.